Whoever has it, it's last call.
I have to stick with.
Okay, that's fine. Okay, we get started here. I want to try and get through 13.7. Just barely here. I'm watching. Has to be handed in by one.
Oh, well, that's just unfair.
Ah, bar's closed. And I went to Nyosa whenever it was. I hadn't been to Nyosa in many years. And anyone go to Nyosa? Were you there when they close? What they do when they close the beer? No, you didn't see that? So like they have like a police officer with a whistle standing there, and then he's counting down, and then as soon as it hit whatever it was, last call was like 10 something, I don't know what it was. He just starts blowing away on this whistle. I mean, and everyone has to like stop in mid-motion, you know. If the beer has not exchanged hands, then anyway, okay. All right, so look, we're gonna get through 13.7 today. We're gonna start 13.8. I'm gonna do two more examples in 13.7 of flux. And to remind you what we have for flux, there are a couple of formulas. The main one I'm gonna use that look familiar? Somewhat familiar? That's what we use. Where we go? There we go. So that's it right there. And this is equal to surface integral over S of F dot N ds, and then this last one, okay? And then we had special cases, all right? So we want to get to this example. Find the flux of the vector field f of x, y, z equals 0, y, negative z across the surface S, where S is the part of the paraboloid y equals x squared plus z squared, with y between 0 and 1, and the disk x squared plus z squared less than or equal to 1 with y equal 1. Use positive orientation. All right, so we have two surfaces that make up S. Let's start with just trying to figure out what those are. So let's start with this paraboloid. Okay, it's like a bowl, but it opens out which axes? This one right here. Opens which axes? It goes out the y-axis. All right, so we have this bowl, it's sideways. Everyone see it? Okay, that bowl, and then we have a cap on it right here, which makes this surface enclose a solid, doesn't it? But that's not, we're not going to talk about that yet. I'm going to call S1 the surface that is created by y equals x squared plus z squared with our y between 0 and 1. And I'm going to draw this out. It's going to look something like that. And remember, our y-axis is coming out of it like this, right? Coming out of the center. And of course, our z-axis goes up, and our x-axis is coming out this way. So that's the picture we have over there. And if we call this S1, then to find the flux, what we can do first is see, is S1 a special case? So is S1 a special case? Well, if you can get one of the variables explicitly in terms of the other two, then it is. And I believe that I could write y as a function of the two other variables, x and z, right? And therefore, it would be a special case. And I gave you that sheet last time, right? Or does this come out of the notes? This is in the notes, right? has the three special cases. So we are looking at the case which is the bottom case right here. And our F in this, our capital F in this problem is this vector field. I'll put it right here. F is 0, y, negative z. That's our P, our Q, and our R, isn't it? That's P, Q, R. And so what we need to determine before I figure out which formula I'm going to use here, or we already know which one, but how I'm going to orient the signs is I need to ask myself whether or not the normal vectors for this surface are going to be pointed to the left or to the right from our viewpoint. So we want our normals in positive orientation, which means out away from the solid that they enclose. If it does enclose the solid, positive orientation is outward, right? So the normal vectors that I want are the ones that would be coming out of this surface like this, right? Those are the normals I want to use. Most important thing to think about on these normals is that the y component of these normals points in the opposite of the positive y direction, right? I mean, they're all tilted depending on where you are on this little bowl, but all of their y components must be negative if they're going to point that way. And so I'm going to use the formula the way it appeared, I think, on the printout, which would be this. The flux integral, this one, is going to turn into a double integral over d. Now, what's d? Because S is the entire surface, right? This curved surface. What is d? No, that's our ds. We're switching our integration here from saying over the surface to over d. It's the circle. It's the actual constraints of the two variables that are controlling y. All right, so d is going to be our restrictions on x and z, which we have not addressed yet. All right, and then it's going to be p times the partial of g with respect to x minus q plus r times the partial of g with respect to z, then with respect to area. We okay with that? No questions? No? All right, let's plug some stuff in here. This should be pretty clean. I'm going to get this thing out of there. All right, so this should become equal to the double integral over d of what's p? 0, that's nice. 0 times, and just for fun, what's the partial of g with respect to x? 2x, right? That's what it would have been, okay? Minus q, what's q? Oh, I forgot. Q is y, right? Plus r times, what's r? Negative z times the partial of g with respect to z, which is 2z. We good? dA. Let's clean up. All right, let's clean this up. So this is just double integral over d of 2x minus y. Oh yeah, sorry, thank you. Negative y minus 2z squared dA. What's that? You want to pull a negative out? Okay, we can do that. Let's see now, can we get some control over our D? So look at D. Go to polar. So what we try and imagine is that we're taking the projection of this surface, right, onto the xz plane. And the reason we're doing xz is because it's a function of x and z. So if you project that onto the xz plane, you should get a circle back there, shouldn't you? So in the xz plane, that circle back there that maps out to that surface has what as its radius? Well, how far out does this bowl go? It starts with y equals 0. That's the smallest coordinate, right? And then the biggest y gets is 1. So if y is 1 in this equation, then that's a circle with radius 1, isn't it? And that's what we'll project backwards. So this should be a circle radius 1. So I should use polar conversion, letting theta go between 0 and 2 pi, and my r should go between 0 and 1. Yeah? Now, what are the conversion identities that I can use here? Like, I can replace what with what here, if I'm going to use the polar coordinates here. I can replace x squared. Anywhere I see x squared plus z squared, I could replace it with r squared. I can replace x with r cosine theta, but not y, right? Not y is r sine theta. It's actually what? Z, because we were in the xz plane. So those are our polar conversions that I'll use. And by the way, what is y? Yeah, remember that because of the way it's written, y is equal to x squared plus z squared, right? If you live on the surface, that's what y is. And we know x squared plus z, this should have been what? Sorry, thank you. This should have been z squared. This should be r squared, right? Understand? So rewrite this now. This integral should turn into, now I can put some limits of integration. How about we go 0 to 2 pi and 0 to 1. Let's pull that negative out, that negative that was in here. And then we have y, right? And what's y, we said? R squared minus 2 times, or plus, because I pulled the negative out, plus 2 times what's z squared? Well, it's this squared, right? So r squared sine squared theta. And then r, right? R, we have to have r, because we went polar, dr d theta. Is that okay? Question?
No, we were saying that if it's a special case.
Do you not do the square root 1 plus the partial?
We did this special case earlier. I think you might be confusing it with surface area.
Oh, yeah.
There was a special case for surface area where we could convert the magnitude of the cross product of the partials of r. I think you're confusing that with this. Which, if you've been doing your homework and you're trying to keep up with this, which I know some of you have been doing, this can all start to get pretty confusing because you get a lot of formulas, a lot of different things that are happening here. You have to know what you're supposed to do. It's not just like grab a formula out of a bag and go, yeah, I'll use that one. You know, looks right. But you see why on the final I don't really even have to ask you a question about a double integral, right? I mean, I don't need to ask you a problem on your final that's going to be like, hey, you know, do this double integral and it converts to polar. I just can ask you something like this and it'll kill all those birds with one stone, right? So it's like 5 or 6 birds with one stone. All right, so now at this point, I don't think I'd want to do the rest of that, but it would be pretty easy to do, right? Can I say easy? I mean, relatively speaking, the r goes through and then you can integrate everything with respect to r. You could also factor an r cubed out and split them. But I'll tell you, if you work this on your own, you should get, as a final result here, negative pi. Let me double check that. Yeah. If you work it out, you should get negative pi. Okay? Now, that's just S1, right? S2 was that other piece, and we have to look at that also. So this was for just S1. All right, so let's look at S2. Now for S2, we had just this part, right? It was that circle that capped off the paraboloid thing. It was like that piece right there. And could I go about this the same way? I could. Can I look at this as being like y is a function of g, or sorry, y is some function of x and z? No? Which part? The disk is an inequality, I agree with that, but do you agree that this disk lies on a plane? What plane does that lie on? It's parallel to the xz plane. It's actually y equals 1, right? Isn't that what it is? And that, you could say, is a function of two variables, x and z. They just don't appear there. And then you could go to the shortcut, couldn't you? It's just that your partials are going to wipe almost everything out. That's one approach. I'm not going to do that approach. I'm going to do something a little different. It's faster, and I think you'll appreciate it. All right, so look at this. Let's take a look just real quick. Because it's a plane, what can you tell me about the normal vectors that are pointing off any point on that plane? Tell me about a normal vector, a unit normal vector that would be coming off of that. What does it have to look like? Any normal vector. A unit normal vector.
1, 0, 1.
Close? Those are all pointing out the y-axis, or the y direction, right? 0, 1, 0, right? All normal vectors would look like that? Do you agree? Yes? Okay. That's only because of the way it's oriented. So instead of using the formula we just used in the shortcut, I'd like for us to entertain this for the first time. I have not shown you one of these yet. That's why I'm doing it. Okay, this right here, and we're going over S2 right now. I'm going to use the formula that looks like this. F dot n ds. So that is one of our formulas. What happens is this ds vector s turns into n ds, where this is surface. All right? The value of this formula is that if you know how this normal vector behaves, especially if it's always the same, then this dot product becomes very easy to compute. So what would happen if I take my vector field, which I erased here? My vector field was 0, y, negative z. If that's my vector field, if I dot that with this vector, what's going to come out? So dot this. Take this and dot this. Just the y, right? That's the only thing that comes out? Agreed? So this turns into this y ds. Are there any questions on where that came from? No? Because I'm not writing it down. I just want to make sure everyone's clear on this becomes y. And then, because you're on this plane, right? Because this circle is on this plane, y'all see the plane I'm talking about? The y coordinate was always 1, wasn't it? So y is 1 always when you're on S2. So this just becomes double integral over S2 of 1 ds. And what is this? This is a special formula when you have a 1 in here. This is the area of S2. That's what this represents. And S2 is a circle, right? S2 is a circle. And what is its radius? 1. So it should be pi r squared. So this should just be pi. With no work. You see that? With no work at all. So can we answer the final question? What is the flux over this surface, the entire surface? It's pi, negative pi plus pi, which is 0. So the flux turned out to be 0.
If the flux is 0, does that mean it's also like the curl and divergence might also be 0, so it's like not moving?
That the curl and what?
Divergence is 0?
Not necessarily. Look, if you take the div of this, look at the div. Here's our vector field. Remember, div is like partial of this with respect to x plus partial of this with respect to y, partial of this with respect to z. Oh, wait, well, hold on. This one you get 1 minus 1. You get 0. Curl. I don't know. We could check it, but
Yeah.
seems like it would make sense that way.
Yeah, that makes sense. Flux doesn't.
All right, let's do another one. This one I'm trying to move a little faster, but I need you to let me know if you're just sitting there going, I just got to get through to next Tuesday. I mean, I want you to understand this, you know? This is like we've reached the end here, but it's a good end. It's like bringing this all together into some pretty cool stuff. All right, look at this object. You have a surface, let's see, you've got, looks like one of those like aircraft hangars, right? All right, so we want to find the flux on this entire surface, S. S is the boundary of the solid half of the cylinder. Z is between 0 and root 1 minus y squared. That draws me basically this and everything inside. And then our x's are stuck between 0 and 2. So the back side of this is x is 0. The front side of this is x is 2. Understand? So 2 planes, the cylinder, and then we also have the bottom. So let's label these surfaces. I'm going to call this one right here S1. The one in the back side there, let's call that S2. How about the one that's underneath right there, S3? And this one right here, let's call it S4. That sound good to you? All right, what can you tell me about S1? It's the face, it's on a plane, right? What's the plane that lives on? X is 2. X is 2, because our x values, x is coming out at us, okay, everyone? So x is 2 is this one. So if I'm going to try and find the flux through that surface, maybe I can do the same thing I just did in the previous example. When we had that flat surface like that, can you tell me about the normal vectors for that S1? If this is positively oriented, meaning normals go out of the solid. What are they? All the normals that come out of this, no matter where you pick, what do they all have common? What are they? 1, 0, 0, right? The normal, so I'm going to write this, the normal vectors for this surface 1 all have this in common. They're all 1, 0, 0. And that means that if I want to find the flux here over S1 of the vector field dotted ds, I could just do this f dot n ds. This one I'll write out. This is double integral over S1 of, what's my vector field here? X squared, y squared, z squared. Dot that with 1, 0, 0 ds. And what does that become when you dot it? X squared. So still have this surface integral, x squared ds. And because we are actually on this surface, right, on this plane, the x value is always what? 0. So we're just trying to do a surface integral of 0, which is 0. X is, oh, sorry, yes. We were doing S1. Why? I said 2, didn't I?
Yeah.
I said 2 and I wrote 0 down. Why didn't y'all tell me something earlier? Okay, that was S2, right, that I was doing there? Say again, yes? This should be what then?
So
4. Go ahead.
the normal vector.
Yes.
Coming out. Could you tell me how it's going to be 1, 0, 0?
Okay.
So it has to do with the plane, but
It's I hat. It's I hat.
so just because of that. Okay. Gotcha.
Right? If I have, I don't know. It's a uninormal vector, yes. That's why it's 1, yes. So you have, x, y, z like this. X, y, z, right, is back there. So this x-axis comes out in the same direction as these blue vectors. So what's a vector that's pointing in the same direction with unit length? That's I hat. That's 1, 0, 0.
Yeah, I was just like.
Well, it's a good question, because if you have that question, I'm sure someone else does. All right. Okay, so sorry about that. X is 0. I was ahead of myself, I guess. That should be a 2, which means when we square it, we get 4, and then we can pull the 4 out. And that's now 1 in there, and this just means surface area of S1, which we should be able to find just by looking, right? S1, if we look at it this way, right, what's the radius? How far out is this? What's the distance from here to here? Well, that comes from this equation, right? Comes from that. That's where it's come from. So to get a z value of 0, you have to plug 1 in, or negative 1. So 1 and negative 1? Yes or no? I could turn it. I'm going to mess up all my stuff, though. Turn it that way. You can kind of see it that way a little bit. Yes?
Okay.
Yeah? All right, so negative 1, 1, and that's my y value. But it doesn't matter. We know that the radius is 1, right? So the area of an entire circle would be pi r squared. Since r is 1, this would just be pi, but we're taking half of it. So it's 4 times half of the area, which is going to be just 2 pi. Okay? Now, let's do S2. S2 is going to be the one that I almost did a second ago. What's the only thing that changes with S2? That becomes 2. That becomes 0. I'm using the same normal vector, right? Because, well, am I using the same normal vector? Hold on. It should point the other direction because they're coming out the back side. You can't really see them. They're back there, and they're pointed out that way on the back side. So they should be what? Negative 1, 0, 0. And then when we go through here, we change this to S2, change this to S2, change this to S2, change this to negative, change this to S2, and this actually, when we dot it, gave us a negative x squared. But that doesn't matter, because at the next step, x is 0, so we just get 0. Questions on that? Okay, so what about S3? What can you tell me about S3 if it's the bottom of this hangar? It's a rectangle, right? What can you tell me? I mean, like this one was, we said this was part of a plane, x equals 2. The back one was x equals 0. The bottom one we could say is z is 0, right? So why don't we do that? We're going to say the bottom, S3, has the equation z equals 0. How about a normal vector for that surface? 0, 0, negative 1, because your normal vectors will be pointing out straight downward, right, off the bottom of that surface. So that would be negative k, k hat. Agreed? This is all still the same. I'm going to dot here, but then this vector changes. And it changes to 0, 0, negative 1. Am I moving too quick, filling in the blanks here like this? Am I? I can slow down.
It takes a little while to.
I understand.
Because we can't read, just erase it.
I understand. I know that. That's why I'm asking. I can slow down.
That's all good.
You're okay? I also am taking into account the fact that this is on video. You know, can always be played back. So, all right, S3. So tell me about this dot product here. What do you get when you dot product that? You get negative z squared. ds, and z is 0. Yeah, so this is going to 0 out again. So we have no contribution to the flux through the bottom of the surface. Yes?
If we needed a negative vector on the y-axis, would it be positive as negative j?
Wait, say again. If we needed what?
A negative vector.
Uh-huh. On the y-axis,
Yeah. So since you use j,
it would be negative j. Yeah.
would that make it positive?
Would that make it positive? I'm not quite sure I follow you.
Like for z, how it was negative 1.
Uh-huh.
So for a negative y, if it needed to be a negative 1, but since you need to put a minus sign for j,
Why am I going to put a minus sign for j?
I'm just curious.
No. J hat is defined to be 0, negative 1, 0. Negative j hat would be that. J hat would just be 0, 1, 0.
Okay, so that's just the top one's just a cross product.
This is just negative j hat. I'm still not following. It's just for cross product? What?
The switching signs and the cross
Okay, I think I understand. When you do your cross product, the middle one always has to switch signs. That's what you're referring to? Okay. All right, we've got 3 of the 4 surfaces. Now, S4 is the most challenging because it's not flat. So the normal vector is not always constant. Do y'all see that? That's kind of like when we see flat surfaces, we like it because the normal is always going to stay the same. But once we start moving around something that has curve to it, it's going to change. So this formula is not as nice. So we'll just go back to the other method. Can you look at S4 in the shortcut, as a shortcut? Can you look at the surface as being a function of 2 variables? Okay? And it's the z, right? The z is a function of which 2 variables? So what's the equation? Sorry. Square root of 1 minus y squared. And of course, our y here is going to be between negative 1 and 1. That's what it took to draw it, right? But that would draw me the surface, wouldn't it? That would draw me the surface. And so I'm going to say that this is a function g of xy is this. And that's the thing I'll be taking partials of. And then I'm going to go and I'll label this is of course my P, my Q, and my R. So I'm doing just what I did the previous example. And which formula am I going to use here? Top one, right? Top one. My normals are pointed upward. Well, do you agree that if I draw normals coming off of this green thing, that the z component is always positive, right? I've got a little bit of a tilt upward on all of these. I'm never, if I was on the bottom side, then I would start to get negative z components. But all these vectors should have positive z components. All right, well, let's go ahead and use the formula then. This becomes, let's see, flux over S4 should become the double integral over d, where d is going to be the restrictions on x and y that draw me this surface. And can you already see what the restrictions on x and y are going to be to draw just this top part? What's the projection of that surface onto the ground? It's a rectangle, so it's going to be a pretty straightforward limits of integration, right? And I'm going to be doing here negative p, which is negative x squared, times the partial of g with respect to x, 0, there is no x in there, okay, minus q minus y squared times, bless you, the partial of g with respect to y. Now that is going to take a little bit of work. The partial of g with respect to y. So if you took derivative of this with respect to y, did some chain rule, you should get negative y over square root of 1 minus y squared. You just trust me that that would be that, right? And then finishing off the formula, plus r, so plus z squared dA. And I'll clean that up. Pardon me? But when you took the derivative of the root, it was 1/2, so I already took care of that. Okay, I'm going to just write this down again. This is going to be double integral over d. This is gone. This becomes what, like negative y cubed over square root of 1 minus y squared? Yeah, negative is plus. Checking out, man, I'm checking out. Plus z squared. Now look, what are the integration variables going to be here? X and y, right? So we can't have a z in here. But do we know what z squared is? Well, that's what z is, right? So square both sides. So z squared is 1 minus y squared. So I'm going to replace this with 1 minus y squared plus 1 minus y squared. And then dA. And I think that's good. I'm ready to go ahead and get my limits of integration. I just want to look at this region on the ground, right? The projection of that green surface onto the ground should create, now just be careful here. This is x, this is y. Remember, x is coming out at you, right? So my x is going to go out to 2. And my y is actually this part, left and right. So negative 1, 1. That. So my restrictions are x is between 0 and 2, y is between negative 1 and 1. So last step I'm going to do is to set up my limits of integration, 0 to 2, negative 1 to 1, of y cubed over square root of 1 minus y squared plus 1 minus y squared dy dx, because I chose the order here to be like this. And if you do this, which I'm not going to do, this one is kind of an interesting integral right here. It's a little interesting. If I were doing that, I would do a u substitution, let u be equal to 1 minus y squared. And I would split my numerator up into y squared times y, and it will work out real nice that way. Another way you could do it is by using trig substitution, but that takes a lot longer. This is a lot cleaner to do it that way. But at the end of the day here, if you do this integral, you get 8/3. So the final result is that the flux of this is the answer from all these surfaces added up, which I think the only other thing that we had that contributed to anything was what, 2 pi? So the final answer to this is 2 pi plus 8/3. That's the flux. All right, good? I have posted the videos for the homework all the way through 13.7. Those were posted as of this morning. So I believe if you look at I think I did 3 flux problems in class. I think I did 4 flux problems on video. I believe that covers 7 problems, and most of them are the homework problems. So I think I've done almost all the homework problems if you take what I've done in class and put it together with what I did online, or on video. And that does it, I believe, for this section, for what we're going to do. What I hope you've seen in these last examples is that, well, maybe if I look at the first example. We did flux on this right here. And when we did this one, we just used the hardcore formula of F dot the cross product of the partials. There was no way around it. There was no shortcut. And we just had to do it that way, and we ground out the answer. All right? That was the first example I did of flux. The next example I did, we realized that the surface could be written as a function of 2 variables, and so we used a special case. And then on the next example, which is what we did just now, we did a combination of a shortcut using the fact that paraboloid sideways could be looked at as a function of 2 variables, and then the very important fact that when you have a plane like this, a flat surface like this, that the normal is always the same, that you can kind of even take an even shorter shortcut to the answer. And then when we got to this last example, there was 3 super shortcuts, the front, the back, and the bottom, and then the top was the other shortcut. You know what I'm saying or not? Okay. Whenever you use the n in the problem, that's a very short way to the answer. But all of these could have been done with the original formula. But then you would have to find a parametric representation for each of these. And then you would have to take the partials and cross them, and it just can be tedious. But you can check it for yourself, it would work out the same. All right, that's it.
Will you be giving a review for the final class?
Just study your homework. Just go over your homework and class notes. That's what I'm going to do when I make the final. I'm going to go through the homework. I'm just going to take a look at.
How many problems though? Do you know?
I have to make it before I can tell you that. I can't tell you if I don't have it made. Okay, so on Stokes' theorem, I thought that we might start this before I even tell you what it is, Stokes' theorem. I thought we'd start with an example, and so that maybe you would come to appreciate it before I tell you what it is. Okay? So here we go. I'm going to go back. This is actually going back to line integrals. So recall line integrals. On vector fields. Do you remember that? And there was a formula for this. This was line integral, and then you were going to take f, you were going to plug in r of t, and then you were going to dot that with the derivative of r dt, and then this is going to give you, you're going to have some restrictions on t, which are going to be your limits of integration. So what we did was, when we had a line integral and we had a vector field, what we did is we found a parametrization of C. So we found a way to draw the curve, and we call that R of t. And then we evaluate the vector field at each of the points on the curve. We dot that with the derivative, right, which is like a tangent vector to the curve, and this somehow gave us our line integral, right? Yes? And then we also said, hey, if you put this here, then you mean that that curve is closed, right? And it's positively oriented. What is positive orientation? Which direction? Counterclockwise, something like that. Okay? So I would like us to start by doing this. I want us to find this. All right, find that for the following. I have a vector field of yz 2 times x times z, then e to the xy. And my curve C is the intersection of x squared plus y squared equals 16 and z equals 5. Yes, I strike my z's. So that's a 2. Yeah. I would recommend, if you don't strike your z's, to strike your z's. If you can't tell your 2's and z's apart, which I can't tell my 2's and z's apart if I don't strike them. Okay. Ready? Let's find a parametrization for this. Let's make sure you understand what this is. This is a cylinder, right? Infinite cylinder. Looks like this. Like that, right? Goes through the, runs out the z-axis. And then we have z equals 5, which is a plane. Z equals 5. Just slicing it. Right, just cutting through and slice this somewhere, and you get that circle, right? That's our curve C. Positive orientation means that as I move along, right, as I move along counterclockwise, which is kind of weird to talk about that in three-dimensional space. Because what if you were looking from the bottom? Then is it still counterclockwise? It's not, is it? You understand what I'm saying? If I'm looking from the top down, it is counterclockwise. But if I'm looking from the bottom up, it looks clockwise, doesn't it? So that throws in some gray area, doesn't it? So what we do is, to get around that, is we say, if this is a closed curve, right? Positive orientation means that if you were to look at filling in between the curve, that as you walk along the curve, the filling, the inside of this is to your left as you walk around it. That's positive orientation. Does that make sense to you? That the surface between the curve, connecting this curve, will be to your left. All right, can you find a parametrization for C? What is that? I mean, that's a circle, right? Radius 4. And that's basically in the xy plane, right? But just moved up. So I could say like 4 cosine t, 4 sine t. And what about my z? It's 5, constant, right? That would draw it, wouldn't it? All right, let's go through. What are we going to need? The derivative, right? So we're going to need derivative of this. Oh yeah, t is between 0 and 2 pi. The derivative of this should also be pretty clean. Negative 4 sine t, 4 cosine t, and 0. What's next? take the vector field and plug in the curve into the vector field and then dot that, not this into the vector field, then dot that with the derivative. So let's go ahead and find what f of r of t is. We'll write that down, and then we'll dot them in a second. F of r of t. I'm just gathering all the information together right now, okay? What is yz? Remember, we're working off of this one. Z is 5, right? Y is 4 sine t. So this is 20 sine t. All right. What is 2 times x times z? So 2 times x times z, 40 cosine t. And then the last piece is e to the xy. E to the 16, right? Because this 16 cosine t sine t. That's f of r of t. And I'm supposed to take that and dot it with that, right? I need to dot those two together and then do my integral, and I should be there, right? Okay, so I'm ready to write this. The line integral over c of f dot dr is equal to the integral from 0 to 2 pi. All right, dot now. Dots are easy, right? This x component times this x component gives me negative 80 sine squared t. I like to see sine squareds. All right, now I do 4 cosine t times 40 cosine t plus 160 cosine squared t. I'm not happy to see the 160. 0 times, that's nice, right? The 0 times this, who cares? That really helped out quite a bit, didn't it? That 0 at the end there. And unfortunately, I cannot use Pythagorean, right? Although, I don't know, you have some choices here. Do you want to like replace your sine squareds with cosine squareds and put it all together, or you want to, what do you want to do? Split this into 2 now? The thing is, if this were negative 80, you could just factor out a negative 80 and then it would just be a 1 and great things would be great. That's not the case. Well, I'll just choose this is what I'm going to do, okay? I'm going to say negative 80. Sine squared t is the same as 1 minus cosine squared t. Do you agree with that? And then plus 160 cosine squared t dt. I'm just trying to get it all in terms of cosine squared. I don't know why, I just felt like doing this. And now pass your negative 80 through. And what would you get next? Integral 0 to pi negative 80 plus what? 80 cosine squared t plus 160 cosine squared t, which is 240? 240 cosine squared t dt. Still good? All right, what do we do when we're trying to integrate cosine squared? Power reduce. So this is 0 to pi negative 80 plus 240, and then this right here becomes 1/2 plus 1/2 cosine 2t. That look familiar? You've done that a million times. Distribute the 240 through. So half of 240 is 120 and minus 80, 40? Okay, so we have 40, and then plus 120 cosine 2t dt. Can you all see that? All right, ready to integrate, finally. Antiderivative of 40 is 40t. And then here, antiderivative, you got to do some scaling. It's going to become like 60 sine 2t, and I'm evaluating 0, 2 pi. When you plug in 2 pi, you get 80t, or not 80t, 80 pi. And then when you plug in 2 pi here, you get 4 pi. Sine of 4 pi is 0, so that goes away. And then you plug in 0, you get zeroed out everywhere, and so your answer is just going to be 80 pi. Okay, so that didn't take us too long, did it? I mean, that was okay? That's kind of like a review of line integrals. So let's talk about Stokes' theorem. Stokes' theorem says the following. It's quite amazing, actually, what it says. I'm going to write it down for you first, and then I'll put it up here with the notes. It says that, let's say that you have a closed curve in three-dimensional space. All right, so you have this closed curve in three-dimensional space. Call it C, all right? And we're going to say positive orientation looks like this. Can you all kind of see that that's like a floating rubber band kind of in space? Well, if this C lies on the boundary of a surface, okay, so that black in there creates a surface, and that C is just the edge of that surface. So it's the boundary. And this is S. And it's oriented in such a way that, like I told you, if you're walking on the red curve, the surface is always to your left. Okay? Then we're going to have the following result. I'm going to tell you what it is in a second. Let me just show you a couple of examples of these that are a little bit easier to follow. What if I just, here's the x, y, z. What if I just draw a circle on the ground? Call that C. Then if I just look at the flat disk right there, does that curve C, or is that curve C the boundary of that flat disk? Yes, right? But I'd like for you to compare that to this. Same C on the ground, okay? But this time look at the upper hemisphere of a ball, okay? So like, you've got this ball up here, right? Do you see that? And if I look at that ball right there, that shell, then C is still the boundary, isn't it? So this surface in between here, S, I'll call it this one S1, and this surface here, S2, are totally different surfaces, right? But they have the same boundary curve. Understand? Here's the kind of mind-blowing Stokes' theorem. Stokes' theorem says that if you want this, if you want to know what this is, which is the line integral around this curve, then all you have to do is compute this surface integral. That's Stokes' theorem. And the reason why this is kind of mind-blowing is because it's saying that to do this line integral, we convert it to a surface integral where the surface S is any surface that has that as a boundary. Which means that if I use this surface or this surface, if I'm trying to find the line integral around C, I can use either one, I should get the same answer. So the surface in the center is totally independent of what's going to happen on that line integral. It's kind of crazy that it works that way. All right, so do I have these? I know I have it in the notes. Let's see how far away it is here. Okay, that was just me reminding you of what the line integral was. And then also I remind you how to do curl, because in the formula, curl is in here. Do y'all remember how to do curl? Okay, I'll remind you when we go through an example. So let's go back to that problem that we had just a second ago. The one that we got 80 pi on. Help me out here. We had a vector field that was what? Y, z, oh, I remember 2x, z, e to the xy. Okay. And we had our curve, which was this guy, like that. That was c, but z was 5, and it came from x squared plus y squared was 16. Is that right? Okay, so it was that curve. It was sitting up here a little bit off the xy axis. There it was, right? So we wanted to do that. We did that. We got 80 pi. But Stokes' theorem says that if this C is the boundary of any surface, right? Any surface. So a natural surface for us to look at here would be that disk in there, right? Look at that disk, that flat disk in there. If I call this S, then what I can do is instead of doing the line integral and doing the parametrization and doing the partial and all that crap, right? Instead of doing all that, I just need to figure out if I can do it's basically you're going to do the flux of the curl instead of the flux of that. That's what we're doing. So we just have to find the curl of this first. So what is the curl of F? Well, that's where you have to set up that weird kind of determinant looking thing. Partial with respect to x, partial with respect to y, good. Partial with respect to z. Then you put your components of f here. E to the xy. And then you do that little determinant thing. So let's do that. This will be a vector, right? Curl is a vector. So we cover up the I components and do a determinant there. So what's the partial with respect to y of this? X e to the xy. X e to the xy. I don't remember that as being my answer. Hold on a second. Okay. No, that's okay. With respect to y, that's this. And then partial with respect to z of this. And it'll be minus, right? Minus 2x. I want to see if any of you can foresee where we're going here. Can anyone tell me the only thing that's going to matter from this curl? And why? The z. Why? The z component. Because we're going to use the fact that this surface has a normal that points up only, which means that the normal is 0, 0, 1, which means when I dot it with the curl, the only thing that matters is the last piece, right? But we'll compute the whole thing anyway. All right, good. Partial with respect to x of this is y e to the xy, but negative, right? Because it's the j. And then, where am I? Here. Here to here, I get y, but it's supposed to be minus, but then it's subtracted. So plus. All right. And then last one, and this is the most important one, right? Partial with respect to x of this, 2z. And then partial with respect to y of this. Is just what? Z, but then subtract it. So minus z. Agreed? So now I'm going to try and find the double integral over s of the curl of f dot ds, I'm going to realize that that's the same as, and please understand, curl of f is just a vector field, right? It's like if I didn't do anything, if we forget this whole other picture and just, I started the problem off, and if I called this f and asked you to find flux, that's where we are. But this is the f we're working with, not that f. Understand? It's the curl of it that we're plugging in here. So I know that this is the same as the curl of f dot n ds, right? Not s vector, s surface area. And I'm using this because I know s has a nice normal vector. And why am I using the one that's up? Yeah, we're going to do positive orientation, which means as we move around like this, that's counterclockwise is positive. We look out to our right, our normals should point up. So what is the normal vector we said? Normal vector is the vector 0, 0, 1, which is k hat, if you like. Now dot curl, so dot that with n, and you just get this, which was just z, wasn't it? So we have the double integral over s of, what did you say? Z ds, that's it. But what was z? Z was 5, wasn't it? Z was 5. So double integral over s of 5 ds. And z was 5 because we were up there, right? And take the 5 out, and this is 1 ds, and that's just the surface area of s. And that, be careful on that, that is pi r squared. What's the radius of that? 4, right? So the radius of this circle being 4 is pi r squared. 16 pi is its area. So we have 5 times 16 pi, which is 80 pi. By no coincidence. So I would say, yeah, there's a little bit of trouble there with the curl computation. You do have to be careful with that. But I do prefer that. I do like that compared, to what I would have done with the line integral. And it's amazing that it didn't matter what you would have used for your surface there. You could have used like a top hemisphere. As long as that was the boundary, it would have still worked. All right. What do y'all think?
What is that answer again?
That's the line integral. Yep. Over the vector field. It's work. It's work. Okay. Yeah. If the field, it depends on what your field is and stuff, but you could look at it as work. Yeah.
When you find the magnitude of the flux vector, what is that going to be? Is that going to be just a scalar of the flux? Is that what it is? Is that
Well, the flux is a number.
So when we find the magnitude, that's the actual flux. So that's what it's going to be.
I'm not sure.
Say that we have that vector, right? We came up with it, the one that you did the determinant for.
The curl?
Yeah, the curl.
The curl of f. What about
So
it?
that's going to be, the magnitude of the curl is going to be the flux, right? So that,
No.
I don't know if there's something I'm misunderstanding.
The magnitude of the curl, the curl of the vector field we're given is the new vector field that we're looking at in the surface integral. All right, let's go now and look at this. I have, I think, 2 examples or 3 examples in here. Okay, let's look at this one and appreciate the work we're not going to have to do. All right, so we have a line integral over C, where C is the triangle with vertices 1, 0, 0, 0, 1, 0, 0, 0, 1, and the vector field is given there. So we have, let me draw it first. Let's draw our curve in three-dimensional space. 1, 0, 0 is here. 0, 1, 0 is here, and 0, 0, 1 is up here. So we're getting like one of the faces of a tetrahedron, right? But just that triangle right there. And we need to move around this C, right? And we want to know the line integral along that. And here's our vector field. Now, if you were not going to use Stokes' theorem, what would you have to do? You split it into three separate curves, right? You would call it like C1, C2, C3. You would have to find parameterizations for each of those curves, which are line segments, right? So we could do this. It's not impossible to do. It's just tedious, right? Then you'd have to evaluate your vector field on the curves, each for C1, C2, and C3. Then you'd have to dot those with the derivatives of the curves. And I mean, it could be done, right? It could be done. Let's see if Stokes' theorem is any easier. So if I'm going to use Stokes', I need to see if there's a surface that's the boundary of. Well, I think just that triangle, right? That surface right there, that triangle connecting the 3 points, that plane, right? It's a plane. That's what I'm going to call my surface S. And I can go a little further. It's flat, so maybe I could find its normal, right? And its normal should always be the same, because it's a flat sheet. It's always pointing in the same direction. I could do that. But at the end of it all, we're going to have to find the curl. So let's see if we can get the curl, right? I'm just thinking through this a little bit, okay? Like, okay, this is a surface. Am I going to have any trouble figuring out what that surface is? No, I've done this before, right? I've figured out how to find the equation of planes. It's not terrible. But the curl part might be a little messy, so let me go ahead and do that. Partial with respect to x, partial with respect to y, partial with respect to z. And x plus y squared, y plus z squared, z plus x squared. I'm going to let you do this on your own. I'm not going to do it up here. You should get negative 2z, negative 2x, negative 2y. So there's our curl. It's not so bad when you work through it. All right. Good. Now? I can find the normal vector, right? Let's see. If I find the normal vector, I'm going to have to do some vectors and cross them, right? I find some vectors. We've done this, right? Way back, chapter 10 is where I first did this, right? So again, I'm going to save us some time. If you were to take some vectors in here across, you would get a normal vector of 1, 1, 1. Here's the reason I'm not going to proceed with that super shortcut. The reason I'm not going to proceed is because what kind of saved our ass last time was that a lot of these got zeroed out, right? And the one that was left always seemed to contain the variable that was fixed, right? Like when x was 2, it turned out to give us 4 times the area of that circle thing back from earlier. Or if x was 0, just zeroed the whole thing out. Do you see that if I do normal dotted with this, do you see that nothing's going to go away nicely? So what I'm going to do instead is I'm going to use this normal vector to come up with the equation of this plane. And again, we could do that because we know all the points, right? This is the normal vector. So it should look like, 1, x minus x naught, 1, y minus y naught, all that stuff. If you do all that, I'll just use this point right here, 0, 0, 1. You get that. And so you come up with x plus y plus z equals 1 when you put them all together. Now what value does that give me? If I know the curl, right, that's my new vector field. And my surface S is given by this equation, what can I do?
Solve for one of the variables.
Solve for one of the variables. Which one would you like to solve for?
Z.
Z, right? Make z a function of x and y. And now you're doing what we started class with. You're doing a special case of a flux problem right now. The only thing that's changed is this, where that came from, right? So I'm doing the following. The line integral over C of f dr has become the surface integral over S of curl of f dot ds, but that has become a special case where I'm going to integrate over d, and I'm using a special formula from 13.7 when my surface S can be written as a function of two variables, which is 1 minus x minus y. That's this solve for z. So there's my special function of x and y. And what's my PQR? Here, right? Don't make that mistake. PQ and R comes from your curl. So this is my PQR. And I'm using, let's see, g of x, y, the top one. My normals are pointed up. Yes?
Why is that a y?
Y is where a y?
Where you dotted the normal with the quick equation?
Where I dotted the... Oh, why is this z? Yeah, sorry, this should be z. Thank you. I did it right here. I just didn't do it right there. All right, so we good? Y'all okay with the normals are pointed upward? The z components of any vector on that plane in that octant there are going to be pointed up a little bit. All right, so I'm using the standard formula, which is negative p partial g with respect to x minus q partial g with respect to y plus r dA. So negative p for us would be 2z, but then times the partial of g with respect to x, which would be negative 1. Then minus q would become plus 2x. But then that's it. Oh no, partial of g with respect to y, which would be negative 1. And then finally, plus r minus 2y dA. Let me clean that up. They're all negative? They're all negative? Do you want me to pull a negative one out or just leave it? Pull it out. Negative double integral over d of 2z. I'm going to leave a space here intentionally. Plus 2x plus 2y dA. This integral can only have what variables in it? X and y, because I switched, right? I'm a special case. That's what z is. So I want to replace this z with 1 minus x minus y. So please remove this 1 minus x minus y, and something real nice is about to happen. I believe the 2x, this is going to give us a negative 2x, and it's going to cancel, and a negative 2y, which is going to cancel, and all you're going to be left in here is a 2, right? So here's where we are now. We have negative, and how about the 2 that's in there? Can I pull that out? Negative 2, double integral over d of 1 dA. And that is the area of D, which is where? It's the base of the tetrahedron, because that D was going to be the restrictions on X and Y, right? And that would have been from looking at the ground and looking at the projection of this triangular plane down onto the XY plane, and it would have looked like this. 1, 1, right? And it would have come across like that. And the area of that is 1/2 base times height, so that would have just been 1/2, right? Times negative 2. So the answer is negative 2 times 1/2, which is negative 1. Understand? Whew, 20 minutes. I was going to give you a chance to work one on your own, but I don't think there's enough time. Did I have the homework up there for that section? That's it, right? I didn't put homework. Okay, what you should do for homework for 13.8. How about 13.7? You know the homework for 13.7, right? Okay. For 13.8, you should do like number 3. Maybe 5, 7, hold on. I think 5, 7, and 9 I did. So number 3, 5, 7, 9 is what I have on here. You can also do 11 and 13. All right, there's one last thing I want to show you since I've got 20 minutes, and this will be nice. We will have one day for divergence theorem. It won't take us the whole class, and we can talk a little bit about the final, and we're going to make it to the end of the book. I don't want to start divergence theorem today, though. All right, so here's kind of a cool problem. I saw this, I found this doing a little bit of research on Stokes' theorem. Let's say that you have a cylinder, okay? And let's say this cylinder has the equation x squared plus y squared equals, now I'll ask you, do you want it to be a general cylinder, or you want me to actually like fix the radius at something? You want to do general? Okay, let's call it, let's not use r because we might need r. Let's just call it c squared. Is that okay? Some constant square. You want to do a? Okay, I'll do a. Just for you. Yes, that's okay. I'll do that. There you go. A squared. All right, now I have a curve, all right? C, which runs along the boundary of this cylinder. Goes all the way around. Starts here at this point, goes around the back side, comes back, and let's call that C, and let's give it that orientation right there. Got it? I'm not telling you what C is. It's any curve that you can think of that does that. Find the line integral over C of f dot dr. Oh, but I've got to get something real quick. Hold on. Got to get you the vector field. And this has to be done correctly, or else it's not going to work. So give me just a second. Y'all can take a break. You can chat with your neighbors for a minute. Okay, you ready? I'm going to give you the vector field. 2xz minus 2y. Two xz minus 2y. Two yz plus 2x. X squared plus y squared plus z squared. All right, I'm going to read this out. Someone just make sure I've got this. First component, 2xz minus 2y. Second component, 2yz plus 2x. Third component, x squared plus y squared plus z squared. Okay. All right, so I'm going to put that vector field over here so it's a little easier for me to work over there. 2xz minus 2y, 2yz plus 2x, and x squared plus y squared plus z squared. That's my vector field, all right? That's F. And of course, this we said was x squared plus y squared equals a squared. A is a constant. C is that curve, right? So find the line integral over this, over that curve with that vector field. All right, so what sort of issues or concerns do you have at this point?
Yeah, the normal.
Do you know what C is? Nobody has given you C, right? Nobody has given you C at all? If you don't know what C is, you can't find a parameterization for it, can you? If you don't know what it is? The best you can do is maybe use Stokes' theorem. But if you use Stokes' theorem, you need to be able to give me the parametric, some way of figuring out what that surface is, right? So you can start working. I'm not saying that the surface in between there, see the curve is not flat, so you're not going to be able to put a flat sheet right across it. You see that? Understand? So there's a whole lot of things you don't know, right? So this seems like almost an impossible problem at this point, because you don't know the parameterization of C, and you don't know anything about the surface between them. All right, so before I continue with this, I just want to show you on the side here a different surface, but it's going to be very similar to that. Let's say we have a cylinder that looks like this. Oh, that's supposed to be straight. Okay, so this we cut the cylinder, right? And this edge is, wobbling around. Okay, so that's kind of like the C is over here. Yes? Got me? And there's a bottom edge too, which you can't see there. Y'all got it? If we are to use Stokes' theorem, then Stokes' theorem says that if C goes around the edge of a surface, right, then we can use the theorem. If I cut a cylinder in two pieces, I actually have two curves that would enclose this surface, not just one. It's the curve on top here, C, which I said is going that direction over there. And then this bottom one down here, which I will call C2. All right, is that okay? I didn't call this one C1, but I'll call that C2, just so there's no confusion. So do you see that C together with C2 enclose the surface? But there's a problem, because in order for Stokes' theorem to work, when you're walking along the curve, right, the surface is supposed to be to your left. Do you agree? Now, if I walk along this curve, is the surface to my left? What's the surface? What's the surface? Right? So let me do this. How about, imagine cutting this and opening it up. That might help. If I cut it and open it up like this. All right, let's say These 2 points come together, these 2 points come together, right? So which direction was C2 in? Is it this way, like this? Which direction is C1 in? Or C? Would it be this one? See, look, what I did is I cut it right here. I cut it, and I just laid it open like this. Right? Hold on. This one is, yeah, this direction. C and C2. All right? You with me still? Now, if I'm walking along C, let's say pointing out towards us is where our head is, up here. The surface over here is to my left, right? But if I'm walking over here, the surface is actually on the other side. So what I need to do is reverse the direction. So how does that affect things? Let me show you. I'm going to write it down. After I write it down, maybe you'll see it. Do you agree, according to Stokes' theorem, that the double integral over S of f dot ds should be equal to the two line integrals? One that would be the line integral, let's say C was okay, right? Orientation, right? Because the surface is to my left. Plus this one, but the orientation needs to be backwards, which means if I reverse the direction, I subtract, don't I? So how about instead I write minus this over C2 f dot dr. Are y'all with me? These two curves, C and C2, enclose a surface. They enclose this surface in here, which is the cylinder. Therefore, the line integrals along those curves should be equal to the double integral over the surface itself. That's what Stokes' theorem says we can do. I had to change the orientation of this curve because I've got to have the surface on my left side. So negative C2 runs that way, which keeps everything oriented properly. Understand? Now, if you said, well, wait a minute, go to the other side of the page, then it's opposite, then I would agree with you, and then all that happens is this one's minus and this one's plus. Okay. Which one? Yeah, they are both closed, actually, because I cut them and opened them up, but that was just to visualize it. These are closed, right? These are closed? I haven't drawn the one over here yet, but the one I drew and erased, they were both closed curves, right? Okay. Y'all okay with this? How's my time? Got 8 minutes. Should be able to do this, I hope. Okay, this is what I'm going to work with right here. I will admit to you, I know nothing about C, right? So there's not a whole lot I'm going to be able to do here. C2 was any curve that I picked that was below it, right? Or above it. It's just a different curve that also goes around the cylinder. What's a nice choice for C2? How about a perfect circle that runs right through the origin, right through the x, y plane, just like that? What if I choose that to be my C2? Right? That I should know about, because I can find the parametric equations for this, can't I? I can draw this curve. It's in the YZ plane, has a radius of A, right? I should be able to draw that. So I should be able to get some information about this, right? That I should be able to get. This, I don't know, but that's kind of what I wanted to know, right? So the only thing really is, can I figure out something about this? Well, all I can hope for, damn it, is that the curl of f, that should be curl, the curl of f is something nice. That's all I can hope for. So you ready to do curl of f? All right, help me out with curl of f. Sorry, you see I forgot the curl f there? You can't, Stokes' theorem's curl, not f. All right, so what's the curl of f? Maybe we can do it without actually, if I just put the stuff up here, maybe we can do it quickly. Okay, so what do we get? Partial with respect to y of this, 2y minus 2y, which is 0. Okay, what about, cover this one up? Partial with respect to x, 2x, right? 2x minus 2x, but change the sign. Who cares? 0. All right, and then this last one, 2 minus 2 minus, yeah, so that's going to be what? 2 plus 2 is 4, right? Be careful. It almost looked like 2 minus 2, didn't it? But it was, what, 4 here? Agreed? All right. I'm with you there. I'm with you there. That's the curl. Now, this is the tricky part. I would have to come up with some parametric representation of this surface now, right? Right? Because I'm trying to do this, ds. Only hope I have is if I can turn that into the n, right? The n. And that is not necessarily easy to do. But I'm going to look at, I want to just erase in here, convert that real quick over to this. Curl f dot n dot ds, or times ds. What can you tell me about that the normal vector of any, if you take any point on that cylinder, what can you tell me about the normal vector? I'll try and exaggerate it. Here's the cylinder, right, in the room. Normal vector is on the cylinder, right? Is going to be any one of these. Now they change as you go around the cylinder. Do you agree? But what do they all have in common? They're all running like this, parallel to the xy plane, aren't they? As I move this thing around, they're all parallel to the xy plane, right? What about the curl of f? Tell me about that vector. It's straight up. And what's the dot product of two vectors that are always like that? 0. Do y'all see that? Yes? That's why it was very important that I pick the right vector field for this to work, okay? This wouldn't work with just an arbitrary vector field. So because this normal vector, when I take the curl of f and I dot it, these two are orthogonal, right? Orthogonal. That means their dot product is 0. And that means the left side is 0. Understand? Okay? So if the left side is 0, then that means that these two on the right side, right, are all that's left. Not that they cancel, they're equal to each other, right? So just move this one to the other side, right? And what you have is that so it's saying the work, basically the work around this curve in this particular vector field is equivalent to the work around this curve. And so now what you would do, because I only have 1 minute, I can't do it, is you would set up this one, because this one we can do, right? R of t equals, we're a cosine t, a sine t, 0, right? That's R of t. That draws me that circle, C2. This is C2. And then I need the derivative, right? Because I'm going to do, this is negative a sine t, a cosine t, 0. And then when I plug this in, I have to plug this into the field, right? And then that, and then dot. It turns out to be nice. I'm out of time. But there's a lot of like